Let's take a look at the evolution of the stable Joule Thief project, which started as a specific project to do with having a nighttime candle. So a solar panel recharges a nickel metal hydride battery during the day, and then outputs to, you can see here it says slow and fast, outputs to a couple of LEDs at night time. The A-Tiny13A is SMD only. There was no plan at that stage to put into a breadboard or use another chip or anything like that, so that's very early days. Here we still see the it's custom built for the candle project. The diodes have gone to SMD. I'm not sure why. The A-Tiny13 is still SMD. This version, again, much the same, still for the candle project. You can see now the diodes have switched to through-hole, but the A-Tiny13A is still SMD. And again, not breadboard friendly and not for any other use. Now this one is just a Joule Thief, so there's no IC on there. It's just put in a rechargeable battery or a so-called dead battery and output a stable voltage depending on the zener. Here the diodes have gone back to SMD. Again, we've got an SMD only IC, but all the pins are broken out, and there's no room on there for the, it's not a specific candle project, there's no LEDs there, you'd have to wire them in. Next version, almost getting there now, so we've got still SMD diodes. The A-Tiny now is not SMD but throughput, although you could put an SMD one in there through an adapter. All the pins broken out, not really breadboard friendly at this stage. And this is the current version, so yes, you can plug it into a breadboard. You can have a through hole, or you can have an SMD IC, and most of the parts are through hole. There's a Schottky diode there now, which makes it more efficient, and just a couple of SMD parts on the back, a decoupling capacitor and a 10K resistor between reset and VCC. So I'm just going to build it now, and I'm going to start with the SMD components on the back. So that's going to be the 10K resistor and the SMD decoupling capacitor, which is 100 nanofarads. Now, I was hoping that when I did this video, if I put the board, the PCB, up on a little bit of a pedestal there, and had it closer to the camera, which is, well, the camera is just an iPad really, sitting upside down on a shelf above the whole workbench there. Yeah, I was hoping that this would be easy to do. As it turns out, because it's waving around probably about, well, 15-20 centimeters above the workbench on an extension alligator clip, it ended up being a pretty stupid idea. So forgive the start of this where I'm waving everything around like a lunatic. In the background there you can see 4.4 volts coming in to a breadboard and an A-Tiny 13A chip, which is hooked up to just do a blinky. It's an assembler program which blinks every I think 4 seconds for 0.5 of a second. So yeah, so the plan is that that's currently operating on 4.4 volts, but using the stable Joule Thief and using this PCB, that will be able to run that same project, but this time from something like, well, 0.8 or 0.9 volts, whatever's coming through from the single AA battery, depending on its state of charge. Alright, so it looks like in the assembly process we've finally got the SMD parts on, so now just going to look at the diodes. That is a Schottky going in, that's a 1N5817. But when I first started, I looked at the circuit as it was online, and it had a 1N4007. And that worked fine for the early variations of this, but in terms of efficiency, there was quite a voltage drop across that. I switched to a 1N4148 at one stage, and that was working fine as well. But eventually with the 1N5817 Schottky, with the low voltage drop through that diode, it ended up being the most efficient solution. So I've also got the Zener in there at the moment. So the Zener, you can vary that, and I have tried lots of different voltages, but I generally find about a 5V1, so that's around about 5 volts plus or minus a bit coming out of that is pretty good for work with A-tiny 85s and A-tiny 13s. But I have had it as low as 3V3, and it works fine. A lot has to do then with where you set the brownout detector, or even whether you have it on at all. And of course, in my case, running with my A-tiny 13 projects at 128 kilohertz, the requirements in terms of voltage and current are very, very low. So, perhaps a Zener of 3.3 is not such a bad idea in that case. But I generally default to a 5V1 and go with that. So that's those two diodes in there, just adding a little bit of solder to the top to make them look pretty, really, because they're actually fine. They're soldered underneath, but a little OCD me says clean it up at the top as well. All right, so we're now looking at the inductor, and that's another whole story too. Looking at the data sheet of the QX5252, the recommendations for the inductor range from sort of around the I think 30 odd microhenry through to about the 300 odd microhenry mark, and I was sticking to that. In fact, I think I was probably around the 60 odd microhenry mark most of the time for the early projects. But again, just in terms of efficiency, lowering the current that's coming through, because the higher that inductor value is, the lower the current that the QX5252 will let through. I ended up switching to higher and higher amounts, and it was a little bit of an experiment actually to see how high I could go before the thing was not functional. And at 470 microhenry, I was getting great efficiency and enough current to still drive projects that just required, like an LED or two. So the candle project runs a fairly efficient 5050 LED. And so, the current requirements for a chip that's just kicking over at 128 kilohertz running a very efficient LED are not that much. So using a large value radial inductor is working pretty well in terms of efficiency. And by efficiency, I just mean that, for very little input in terms of solar power, the candle project, for instance, runs all night. This is the 47 microfarad capacitor, electrolytic capacitor, and that's just for smoothing, really. So, in the circuit, that just is helping to provide a smooth DC output, because the QX5252 does provide an oscillating output. Most of my measurements in that regard have been around the 140 kilohertz, and if you look at that, that signal, it's fine if you want to run something like an LED, because it flickers so much. Of course, you're not going to pick that up with your eye anyway. But in terms of being more stable for running a microcontroller which has got code on it, then of course, the more stable the voltage, the better. So part of that is the output is the capacitor. There's not only the 47 microfarad capacitor, the electrolytic capacitor, but there's also a little 100 nanofarad SMD capacitor on the reverse side, and that's basically decoupling between VCC and ground. So the combination of those two makes for a very stable output from the QX5252, which is good. That's what the microcontroller wants. Now I'm just putting in here a pair of 4-pin female headers. It's basically a socket. I've also put in a DIP8 adapter from in other versions of this, and that works fine as well. It's really a bit of a matter of personal preference, but any any way that you can plug a chip in. You can plug it in directly, but programming it after that is a little problematic. So I tend to have chips that I can pull out and reprogram if I need to. And the whole idea of this is actually that you can use this for prototyping. So you can pull out chips and put them back in again, such that you can use it to prototype a project and do your development. And then I guess in the end, if you were happy, you could eventually just solder in directly your through-hole IC. So now we're just putting in the male header pins, which will plug into the breadboard. So all of these, and I don't know why I didn't do this in earlier versions, but all of these pins now, the one for the battery, the ones for the solar panel, and the breakout pins for your IC, they're all of a length that fit neatly onto a breadboard, making it breadboard friendly. So yeah, that's a good thing. And now I'm just soldering on there the pins for the solar panel. So we're getting very close to completion, and then we'll just test it, and then it's good to go. So because this is evolution, I'm pretty confident about the characteristics of this circuit now in terms of being able to provide something useful, and only, as I said, for small projects like that A-Tiny 13 at the back there that's been flashing away through this build. Uses very little energy, and so this little stable Joule Thief platform works fine. And that's pretty much it. It's complete. So I'm not sure how long that took. Probably around about 10 minutes or so. Now I'm just going to plug in. Now initially I would plug it into where you would normally plug in VCC, which is pin 8, and also plugging into ground. But that is not, because it's only a single AA battery, that is not going to provide enough to actually run this. So put the chip in, and then grab the LED, which I've got an integrated resistor with that, but not working, nothing coming through, even wriggling won't help. So I'll plug that LED in a little better, and then we'll use the actual input for the battery, just a single AA battery, so that feeds into your QX5252, and now we have that actually flashing away. So that's the A-Tiny 13 asleep for 4 seconds, and then flashing, I think it's quarter of a second or half a second, and that's running off a single AA battery. But it's providing, through the QX5252, it's providing your 5 volts ish, stable enough to be able to run code. So just zooming on that a little better, and then we'll just do a little bit of testing. I'll show you some of the voltages at various points. So this is the battery coming in at 0.85. The 5 volts you see in the background is just for the actual voltmeter, so it doesn't go to the board or the chip at all. And this is measuring now the output of the QX5252 via the Zener and Schottky diode, and that's a stable 5.1 volts, and that's the circuit working. So yeah, pretty handy little PCB, lots of development. Maybe not the last time we'll see it on this blog.